Good morning, students. Today we are going to see one of the fundamental problem of quantum mechanics, that is particle in a box. The particle in a box model describes a particle which is free to move in a small space surrounded by impenetrable barriers, representing the fundamental quantum mechanics problem where the potential energy inside the box is zero and it is infinite outside. Let us go into the problem. As I told you already, the particle inside the box problem is one of the simplest but very important applications of Schrödinger equation that illustrates many of the concepts in quantum mechanics. For a particle moving in one dimension, say along the x-axis, the Schrödinger equation can be written as h cross squared minus h cross squared by 2m psi double dash of x plus v of x psi of x equal to e psi of x. You understand that looking at this equation, this is the Schrödinger equation in steady state form. In the last class we have seen and we have derived it. This is the Schrödinger time independent equation, or what we call as Schrödinger equation in the steady state form. So now we are considering a particle that is residing within two endpoints. That is, there are two boundaries, x equal to 0 and x equal to L, and there is a particle that is captured within these two boundaries. This particle cannot cross over these two boundaries. I told you the particle cannot pass through these walls. Why did I say that? Because the potential energy is zero within this region and it is infinitive at the walls, that is at x equal to 0, x equal to L and outside of it. So the potential, the particle that is residing within this wall has zero potential. In order to cross over this wall, this particle should possess infinite potential. Unless and until it has that infinite potential, it has to reside within the wall itself. It cannot cross over. Therefore, we can say this is a potential well problem. Therefore, the particle is a bound particle within the potential well. And the boundaries are, as I told you, x equal to 0 and x equal to L. Therefore, the wave function is equal to 0 at x is less than or equal to 0 and x is greater than or equal to L. That is, the wave function is 0 in this region, and at the boundaries. That is, at x equal to 0 and x equal to L. Now, our task is to find what is psi within this box, that is, between these two boundaries. So, let us now proceed to find what is psi value in the coming slide. Now, in the Schrödinger time independent equation, the potential energy term becomes zero. Why? Because the particle that is captured within the potential well has zero potential energy. Therefore, this Schrödinger time independent equation is reduced into minus h cross squared by 2m psi double dash of x equal to e psi of x. This equation can be written as psi double dash of x plus k squared psi of x equal to 0, where k squared is representing 2me by h cross square. Now look at this equation 5. This equation 5 has a general solution that can be written as psi of x equal to a sin kx plus b cos kx, where a and b are constants that are to be determined by the boundary conditions. Now we are going to apply the boundary condition to the general solution. We know psi should be equal to 0 at the boundaries and outside. So now let us take the two boundary condition, that is x equal to 0 and x equal to L. Let us take first x equal to 0, the first boundary, and apply to the general solution. So psi should be equal to 0 at the boundaries. So when we apply the first boundary condition, psi should give us a 0 value. Therefore, wherever x is there, you substitute the value of 0, because the boundary condition we are applying is x equal to 0. So therefore it is psi of x. In the place of psi of x, we are substituting psi of 0. It should give us a 0 value. When it is applied to the general solution, a sin 0 plus b cos 0. We know since sin 0 equal to 0, the first term automatically becomes 0. But second term doesn't, cos 0 equal to 1. So it gives us a b value. But according to the condition, psi should be equal to 0 at the boundaries. So in order to make it 0, one condition is that the b should be equal to 0. Hence, we conclude b equal to 0. Now, the second boundary condition we are going to apply is that x equal to L. That is the second boundary. When we apply the second boundary, we get psi of L equal to a sin KL. The second term becomes automatically 0 because we have assumed b to be 0. Now we can also assume a to be 0. But if we assume a to be 0, psi of x would be everywhere 0 and the particle would disappear. It will give us a trivial solution. Therefore, here in this case, we are assuming a is not equal to 0. Therefore, it becomes psi of L is equal to a sin KL. Since we have concluded that the a value is not equal to 0, then the sin KL value should be equal to 0. That means KL value should be integral multiples of pi. We know sin pi is equal to 0, sin 2 pi is equal to 0, sin 3 pi equal to 0. Therefore, KL should assume the values of n pi, where n is the integer, takes the value of 1, 2, 3, etc. Now we are going to eliminate k from the equation 6 and 10. What is equation 6? It was k squared equal to 2me by h cross square. Now in this equation, we are having the e alone one side and bring out to the other terms to the other side. Therefore, e is equal to h cross squared k squared by 2m. So, when we are now substituting the values of k squared here in this equation, the expression becomes En is equal to h cross squared pi squared by 2ml squared into n squared. And we know h cross is nothing but h by 2 pi. Here h cross squared is there. So when we write the expression in terms of h squared, the expression becomes h squared by 8m L squared into n squared. So these are the only energy values which allow the solution to the Schrodinger equation, which is in consistency with the equation 2, boundary condition 2, where n is the quantum number. Here we have drawn the energy level diagram corresponding to n values, n equal to 1, n equal to 2, n equal to 3, etc. For n equal to 1, the energy value is pi square h cross square by 2ml square. When n equal to 2, that is first excited energy state, the energy value is 4 pi square h cross square by 2ml square. Similarly, for n equal to 3, the energy value becomes 9 pi square h cross square by 2ml square. So, in the previous section, we found that the wave function of the particle in a box whose energy E is given by psi of x equal to a sin kx. Here k is nothing but root of 2me by h cross square. Therefore, when we substitute the value of k in the wave function, it becomes psi of s equal to a sin root of 2me by h cross square into x. We know as we have derived the energy value from the previous section, we know that En is equal to h cross square by 2ml squared into n square. Now, we are going to substitute those value and simplify this equation which gives us the value psi of x equal to a sin n pi x by L. So, this is the eigenfunction corresponding to the energy eigenvalues En. Since the value of A is arbitrary, it can be adjusted so that the wave function is getting normalized. We know the normalization condition, that is the integral over the two boundaries should be equal to 1. So, integration over 0 a, where these are the two boundary condition, psi n of x the whole square into dx equal to 1. This is the normalization condition. Now, in the place of psi n of x, we are going to substitute equation 4, which we have 14, which we have already derived in the previous slide. Therefore, the equation 15 becomes a squared, two boundary condition 0L, sin squared n pi x by L into dx equal to 1. So this is the normalization condition for this case. Now we are going to explain clearly how the integration is done step by step. Now let us take sin squared theta. You know how sin squared theta can be written as 1 minus cos 2 theta by 2, where here in our case theta is standing for n pi x by L. So in the place of theta, when we substitute n pi x by L, it becomes 1 minus cos 2 n pi x by L divided by 2. So the integration part is integral over 0 to L 1 minus cos 2 n pi x by L by 2 into dx. 1 by 2 is a constant term, so it can be taken out, so that we have within the integral 1 minus cos 2 n pi x by L into dx. Now let us take the integration part alone and take the dx inside and multiply it. Therefore, it is 1 by 2 integration over 0 to L dx minus integration over 0 to L cos 2 n pi x by L into dx. So now we are going to integrate the term. Let us take the first term. What is the first term? It is 0 integral over 0 to L 1 into dx. When we integrate, we get as x. When we apply the limits, that is upper limit minus the lower limit, we get L minus 0. The first term becomes L. Let us take the second integral term, that is integration over 0 to L cos 2n pi x by L into dx. When we integrate it, we get L by 2n pi sine of 2n pi x by L. Apply the limit, upper limit minus the lower limit, we get L by 2n pi sine of 2n pi L by L minus sine of 0. This second term becomes 0. The first term L get cancelled, so you have sine of 2n pi. We know sine of integral pi is equal to 0. So that term also becomes 0. Now the second integration term completely becomes 0. Only the first term remains. So when we substitute in the original equation, it becomes 1 by 2 into L minus 0. The answer will be L by 2. So the integration over 0 to L sine squared n pi x by L into dx gives us the value L by 2. From equation 16, that is a squared integration over 0 to L sine squared n pi x by L dx equal to 1. We have just now found the value of the integration term for this term as L by 2. So from this we can identify the general normalization constant, that is A. So when we substitute A squared L by 2 is equal to 1 and keep only A squared this side, it goes as 2 by L the other side. So we want the normalization constant A. So A is equal to root of 2 by L. For all values of n, the value is A value is the same. Finally, we can write the normalized eigenfunction as psi n of x equal to root of 2 by L sine n pi x by L, where n will be taking the values of 1, 2, 3, etc. In figure, we have given the probability density distribution, that is mod psi n of x squared for the quantum particle in a box in the ground state n equal to 1, for the first excited state n equal to 2, and the 19th excited state where n takes the value of n equal to 20. So today we have seen in detail the particle in one-dimensional box. I hope you understand, students. Thank you very much.